Single-photon avalanche diodes, or SPADs, are novel image sensors that are sensitive to individual photons and can record the arrival of photons with picosecond precision. Till a few years ago, SPADs were only available as single-pixel or small arrays such as 32 by 32 pixels. While they showed promising performance in lab settings, they were largely restricted to static and relatively simplistic scenes. Fortunately, the resolution of SPAD arrays has improved rapidly, which, for the first time, allows capturing high-frequency spatial details needed for general computer vision in the wild. But one challenge here is that SPADs capture a stream of binary frames with sparse detection of photons. It is nearly impossible to understand what is going on in the scene from a single frame. Therefore, we need to combine information from a binary sequence before we can perform downstream computer vision tasks. Existing SPAD cameras simply add binary frames captured over time into multi-bit images by using on-chip counters. Although this approach works well for static scenes, it suffers from the blur-noise trade-off. The result images are either too noisy or too blurry, and the downstream algorithm, for example object detection, fails to work. Inspired by burst photography for conventional cameras, it is possible to measure and compensate for the motion between binary frames and combine them into a single multi-bit image with reduced noise and blur, which can be used by the downstream algorithm. We call this scheme quantum burst vision. In this example, the person is successfully detected. Notice that conventional cameras do not always benefit from burst photography, as each frame suffers from a fixed amount of read noise. This can ruin the actual image signal in each frame in challenging low-light, high-speed scenarios. In contrast, SPADs have negligible read noise. Therefore, they are the ideal sensor for low-light burst vision. In this work, we focus on using burst vision to explore quantum vision in the real world. We capture data using a real SPAD array, which are not restricted to one or two proof-of-concept tasks in controlled lab environments. Instead, we capture binary sequences for 9 different downstream tasks, which cover a wide range of lighting conditions, scene or camera motions at various speeds, in both indoor and outdoor environments. The total number of binary frames in this dataset is more than 50 million. Besides object detection, burst vision can be used for recovering semantics for a variety of tasks, including background subtraction, human pose estimation, face detection, and action recognition. In addition to recovery of high-level semantic information, many computer vision tasks also involve the recovery of high-frequency spatial details. In this example, we show a fast-moving QR code in a dark environment. Naive average generates noisy and blurry results, while burst vision gives a clear image where the QR code is correctly decoded. The same sequence is also used to evaluate syntax detection and recognition. Similarly, burst vision gives a sharp image for text detection. In this sequence, we use SLAM to recover the handheld motion of the SPAD camera in a dark room. At first, the scene is illuminated by the lamp, and the tracking works properly. When the lamp is turned off, the scene is extremely dark, but the reconstructed images still contain clear features that can be used to track the camera motion successfully. So far, we have shown that quantum burst vision enables various computer vision tasks in the dark. But how does SPAD compare to other low-light sensors? Here, we capture synchronized object tracking sequences from 3 different cameras. The night vision camera suffers from motion blur and object tracking fails. The thermal camera gives a clear image but does not capture visual features in the visible light spectrum. The SPAT sensor generates a clear, blur-free image for robust tracking of the ball. We would like to emphasize that this is not meant to be a direct comparison between camera technologies, as they have different sensor sizes, exposure times, and optics. Instead, through this example, we show that there are extremely challenging image conditions where current imaging technologies still struggle at, while SPATs may provide a potential solution. In addition to indoor scenes, we also evaluate the capability of quantum vision in challenging outdoor scenes. We fix the SPAT camera and the night vision camera side by side above the dashboard of a car, which is driving on a street without any street lights. The SPAT is able to detect the pedestrian from a longer distance than the night vision camera, even beyond the reach of headlights. In another sequence, we run SLAM to track the trajectory of the car. SPAT is able to track the motion and reconstruct a map despite the dark environment, while night vision camera fails to track due to noise, blur, and low contrast. SPAT works not only in dark environments, but also in environments with high dynamic range. This sequence starts from a dark room with illumination down to 1 lux, and gets directly exposed to sunlight at the end at about 50,000 lux. Burst vision is able to generate images with high dynamic range and detect the person across the entire sequence. Note that the exposure time and aperture is kept constant throughout the sequence, which means that the camera can adapt to an even wider range of lighting conditions if auto exposure is implemented. In summary, we demonstrate the performance of burst vision in the wild for a wide range of downstream tasks and challenging imaging conditions. We'd like to emphasize that, in the long run, explicit burst reconstruction may not be the optimal approach to quantum vision. Our aim is to use this approach as an example to bootstrap the exploration of quantum vision, which will hopefully spur further research in this young but promising subfield of computer vision.